চেয়ে নিচ্ছি। আর ওয়েবিনার শুরুর আগে বলছি সবাইকে যারা আছেন অডিয়েন্স এবং পার্টিসিপেন্ট, আমরা ওয়েবিনার চলাকালীন সময় আমাদের মাইক্রোফোনটাকে অফ রাখবো। হয়তো শেষের দিকে আমরা আপনাদের কাছ থেকে কিছু প্রশ্ন উত্তর নিব, যেটা আপনারা চ্যাট বক্সে করতে পারেন, কিংবা ওই সময় আনমিউট করে আপনাদের সরাসরি কোশ্চেন আমাদের স্পিকারকে করতে পারেন। তো লেটস স্টার্ট। শুরু করতে যাচ্ছি আমাদের আজকের টেক সেশন, webinar on quantum computing, hosting by IEEE Computer Society Student Branch Chapter IUB in association with Department of Computer Science and Engineering IUB. আজকে আমাদের সাথে উপস্থিত আছেন মিস্টার সাদ্দাত হাসান। আসসালামু আলাইকুম স্যার, কেমন আছেন?
ওয়ালাইকুম সালাম, I'm good. আলহামদুলিল্লাহ।
স্যার, প্রথমেই শুরু করতে যাচ্ছি আপনার ইন্ট্রোডাকশন দিয়ে। কারণ আমরা জানি আপনার আন্ডার গ্রাজুয়েশন কমপ্লিট করেছেন আপনি ব্র্যাক ইউনিভার্সিটি থেকে, বোথ টু মেজর সাবজেক্ট কম্পিউটার সায়েন্স এন্ড ফিজিক্স। তো আপনার এডুকেশন লাইফ, ক্যারিয়ার লাইফ, এই জায়গার পুরো হোল জার্নিটা আপনার কাছ থেকে আমরা জানতে চাইবো এখনই শর্ট ভিউ। স্যার, আপনার ক্যামেরা টার্ন অন করতে পারেন।
আপনি কি দেখতে পাচ্ছেন? হ্যালো, হ্যালো,
শোনা যাচ্ছে।
আমার ক্যামেরা কি দেখা যাচ্ছে?
দেখা যাচ্ছে না স্যার। স্টপ প্রেজেন্টিং। হ্যাঁ, এখন ঠিক আছে।
Okay. So, assalamu alaikum everyone. I'm Saddat Hasan. So, I'm from BRAC University and I have double majors in computer science and physics. And my senior year thesis was in quantum computing and analysis of quantum algorithms. Till now, I'm pursuing that thesis. And right now, I'm studying quantum information theory with black hole information paradox and Hawking radiation. And recently, I have diverted my interest to quantum machine learning. I'm just exploring these things, and let's see where it takes me. So, yeah, that's basically that's the intro of me right now.
তো আমাদের প্রথম প্রশ্ন যেটা, যেহেতু আজকের ওয়েবিনারটা হচ্ছে কোয়ান্টাম কম্পিউটিং নিয়ে, তো ফার্স্ট কোশ্চেন, হোয়াট ইজ কোয়ান্টাম কম্পিউটিং? আমরা এটা কি কাজ করে, এটা দিয়ে আমরা কি করতে পারি? তো এই পুরো বিষয়টা নিয়ে আমরা স্টেপ বাই স্টেপ আপনার কাছ থেকে শুনবো। তো শুরু করছি স্যার।
So আমার আসলে আচ্ছা, so should I start the presentation right now?
Yes, sure.
Okay. আপনারা কি আমার স্ক্রিনটা দেখতে পাচ্ছেন? স্লাইড?
হ্যাঁ, আমরা দেখতে পাচ্ছি।
Okay. First of all, thank you very much, IEEE Computer Society Student Branch Chapter IUB for inviting me to present today. This is a webinar, Quantum Computing for Everyone. If you are wondering why this is true, because I have given another lecture on quantum computing for everyone in my university, and this is the so this is like part 2 of that. Like I'll be dragging some things from there, and I have added new things in the slide, so I'm just putting it right away. I designed the presentation today basically for everyone to understand it with a little bit of knowledge in simple mathematics and calculations. I hope all of you will enjoy, and let me know when I start boring you guys, because it can go sideways. Anyways, so let's start. So I'll be talking about basically two things. First, I'll talk about why quantum computer and why this is a hype and why everyone is investing billions of dollars in quantum computer and stuff. And on the later part, I'll be talking about how does a quantum computer work. And basically that will be a bit technical with a simple like mathematics and stuff. Nothing fancy and nothing like there is nothing to like I tried not to put something that will bore you and stuff. So let's see. Also, please let me know if you can't like hear my voice or anything like that. So yeah. So let's see. Let's talk about like some problems, like the major problems that we face nowadays, like the protein folding problem, the climate change, Alzheimer disease, AIDS, efficient yet cheap batteries, financial market predictions, large integer factoring, and database search. These are the problems that we deal with day to day, and these are some of the problems that we haven't yet solved with classical computer, like the protein folding or climate change, and like the like basically protein. If we can like find an efficient way to protein folding, then we'll be able to design effective medicine for every disease like Alzheimer, AIDS, and cancer. And maybe if we had like better computer or better way to compute these problems or better algorithms to uh, like better algorithms to solve these problems, we could have like solved uh, vaccine for COVID-19. So yeah, that would have been really cool if we had a workable quantum computer. I'll tell in a bit why that quantum computer can like target these problems. So uh, and also the large integer factoring, this is one of the most like prominent problem that like the world is working on right now with quantum computer. They are trying to approach this problem with quantum computer, and they have solved it. And also the database search and financial market predictions. These are like pretty complex problem which we cannot solve in a classical computer system when the computational power which is needed is like it's tremendous. It's like exabytes of calculation needed to be done in a second or a split second. So why do we need quantum computer? Let's look at the complexity spaces. If you are not familiar with this diagram, it's completely fine. I'll just explain what's happening here. So the problems that we can solve with classical computer in polynomial time or in like basically just think of it like solving a problem that relies on the p problem space. That is like the p problem, the greenish circle. All the problems that we can solve with classical computer, those are in this space. And there are higher order spaces like the NP complete. If you are familiar with P and NP, then you will know what I'm then you will have idea where I'm going basically. The NP complete is like the NP complete problems that we cannot solve with classical computer, and like there is no viable way, or there is no algorithms that can encounter an NP complete problem. And there are other problems like higher order problems like P space problem, which are out of this boundary, like the uh, purple boundary, and those problems are also cannot be solved with classical computer. But when the idea of quantum computer came, there are some problems which are not basically NP complete, but which we cannot solve with the current power or the current calculation speed of the classical computer, but that relies on that like just floats and like right outside the boundary of P problems. So if we encounter those problems, we cannot solve those problems. We can just say if this problem is solvable or not, if it's solvable or not, or if we can get any right answer or not. So, but when the idea of quantum computing came, there is this like dotted area that you can see that's called BQP. That's like bounded error quantum polynomial type. That means like the bounded error quantum polynomial times, it's greater than p, but it's not like up to NP complete. So what happens here is like this is also a part of the NP problems. There are some these problems we can solve with quantum computer if we have a viable quantum computer, if we have a computer that pure quantum, not adiabatic one. I'll talk about it later what pure quantum computer means. And if you see on the like bottom of the picture, I have written a set notation that says all the P problems are in the BPP. BPP means bounded polynomial time problems, and then all the BPPs are inside the BQP. What I mean by BPP is that outside the P problem zone, there are like these purple area, which is not like solvable by classical computer, but those are problems that if we have like a powerful computer, we can encounter it and we can find a solution to it. So these problems are BPP complex problems, and we can solve it by they already rely on like they already are in BQP. So we can solve theoretically we can solve it with quantum computer because till now we don't have a physical quantum computer or working quantum computer. And then there is this polynomial problem space, which is higher class than BQP. And then this P space, you can all see that P space, it's like covering all other problems. So maybe with quantum algorithm or like quantum simulation, we can someday solve all these problems. Uh, this is basically this diagram shows why the quantum computing race is happening right now, because all these problems that falls inside the BQP, those are problems that people are trying to solve for long, uh, 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 like the problem of large integer factoring, like protein folding, finding the correct element for battery, which is cheap yet highly efficient, and like the answer for cancer and answer for Alzheimer's disease and stuff. So these are the problems that people are trying to solve, and they have got a new tool that is quantum computer, which can be used to solve all these problems. And now they are up to that, and that's why they are rushing towards that. Let's see what quantum supremacy war that has been going on. So, like Google, NASA, Intel, IBM, and all the tech giants are investing like billions and billions of dollars in quantum computer research, and they are. It's like they are racing each other to achieve quantum supremacy. So, what is quantum supremacy? Quantum supremacy is nothing but the fastest classical computer that exists on Earth. It has some boundary that it can execute like some number of exabytes of calculation in a second or something like that. So if you can achieve the quantum supremacy, that means you have a number of working qubit which can outperform the fastest classical supercomputer that exists right now. So if you can solve this, then you have like gained quantum supremacy. And uh, recently, recently, Google announced that they have like achieved quantum supremacy with I forgot the number of qubits they talked about. They achieved I maybe 52 or something, but yeah, they claim that they have achieved quantum supremacy, and they can outperform the fastest supercomputer that exists right now. And that's what's the name of it? I think Tai Taigen or something. It's in China. Okay, let's go forward. So, what are the known applications that we can do with quantum supremacy? So, what we are going to do is like factoring large integer. So what will we achieve by factoring large integer? Like we know that our banking transaction and all other like transaction that we see that we use nowadays all are encrypted. And what's the like secure encryption model right now? It's the RSA encryption. It's a for like I personally use RSA encryption for my PGP key, and that's like 4096 bit of encryption. So So it's a huge. It's like with a classical computer, it will take years to solve, years to like find out the private and public key, like factoring that large integer. So, but for quantum computer, like it will take like up to maximum like few hours or so. Like if a classical computer can encounter this problem and solve it within like 10 to 12 years, for my estimation, a quantum computer can do it in 5 to 6 hours. So that's the difference between a classical and quantum computer. Quantum computer, and classically, it has only been like um 2048 bit RSA, which was cracked like 2 3 years back, and that was cracked by the NSA supercomputer facility. And now, I think Google and NASA are working together to like beat that number, and they are trying with like 3,000 something bit of encryption with like RSA encryption. So they're trying to break it basically. So what will happen when you break a classical encryption code? That means you have no privacy, you have no security. So it will be just a mayhem to the like banking transaction and stuff, because there will be no security that can that you can use to transact to send money, or like to encrypt your privacy. So why are people rushing towards it? It's like more of a like superpower thingy. If you can remember, the 5G supremacy war was like literally now it's going on between uh, China and USA. So they are fighting against like who is going to like implement 5G faster, and they will have all the data for himself and the country itself, and they will use it to do whatever they want. It's like the same. If you can solve, if you can crack the RSA encryption, then you know what's happening in the world. There is no encryption that can, there is no basically classical encryption that can like hide information from you. But we have like the researchers and the scientists who are working on it. We have another solution, that's quantum encryption. So yeah, so if the RSA is like broken, then we'll just shift to quantum encryption. So that's the relief that we're not totally doomed right now. And also for like Grover search algorithm, these are like Shor's algorithm, which is used to like factor large number. That's the very first algorithm, the very first quantum algorithm. And then comes the Grover search algorithm. Grover search algorithm is a very powerful tool. It's like if you have like an unordered database, like that's no way ordered, it's a chaos. And it's like you like for a classical computer it will take years to search a thing. Like if you search something there, it will take like years in like computer time. But for a quantum computer with Grover search algorithm, you can do it o cube root of n. So, oh, I think there is a typo on my slide. I'll fix it. Sorry about that. It will be cube root of n time. So that's basically like well, logarithmically smaller number in time. And it is also believed that it can exponentially speed up. Like for quantum computer, it is also believed that it can speed up to simulating quantum mechanical system, which will lead us to like protein folding and like atom connecting atoms and chemical reactions and stuff for like battery and other researches. Like recently I was reading one article that says there is one problem that quantum computer can solve right now, that is how much energy that a plant need to produce its like fruit. So that I think a classical supercomputer was calculating it, but it failed. Now two scientists have like hypothesized some theory that it can be solved with quantum computer with, I don't know, 110 qubit or something. It's not a published paper; it's just a blog where I read it. So yeah, that's it. That's the basically that's the applications of quantum computer. That's why people are working for it, and that's why people are investing so much money behind it, and they can achieve quantum supremacy and stuff, and they can like solve all these problems and be ahead of the other in the race. So yeah, uh, So that was why we need quantum computer. And if you have any other question, I'll be happy to answer it after this, like after I finish my presentation. Let's go to how it works. So things we're going to need here, like we're going to represent computational basic linear algebra. Like it's nothing. If you are familiar with metrics, you will be fine. I'm not going to take you somewhere where you don't like where the environment is not like suitable for you, or I'm not gonna speak in Klingon, so that like stuff and everything. So we'll be talking about reversible computing, qubits and superpositions, quantum logic gates, quantum logic operations, and we will basically at the very end we will outperform a classical computer by algorithm that I will talk about later. Let's jump into how it works. So we all know that the classical computer works like zero and ones. Like there are only two bits, either it's zero or one. It can only be one phase at a time. Either it's zero or one. It's you can think of it like a switch, electric switch. Either it's off or on. If it's on, the light glows. If it's not, the light is off. So that's it. So one bit with the value zero, we can represent it with a fancier notation, that is Dirac vector notation. That's the Kate notation. You can see in the first line, also written as Kate zero, which is Dirac vector notation, and that can be represented in matrix form, that is 1 and 0. It's a like linear matrix, and 1 0, and then we have like the bit 1, which can be also represented as like Dirac vector notation ket1, and that can be also written as 0 and 1. And remember these two things because it's gonna help you like go further in my slides. So just yeah, and this is just simple matrix multiplication. I think we all did it in our high school and in our first year or second year mathematics course in university. So this is basically how you multiply two metrics, like square matrix or linear matrix and the square matrix. This is it. This is it. This is like the whole game here. There is nothing new to know. Just if you can do this, you are good. You are good to understand how a quantum computer works. So now let's talk about some bit operations. If we have like, this is also super easy to understand. Suppose you have a function or a box. You put a classical bit 0, you will get a 0. It's an empty box. So if you put 1, the output will be 1. So it's called the identity operation. So why it is called the identity operation? Because the input that you are giving, it's not being changed. Like it's not changed in the function or in the box. You are putting 0, you will get a 0. You are putting 1, and you will get a 1. And the negation operator is just the opposite of identity operation. What it does, if you put a 0, it will return you a 1. And if you put a 1, it will give you a 0. This is it. And this is like the identity matrix 1001. And if you remember in the last slide, we represented 0 as 1 0 and 1 as 0 1. So what we are doing is we are multiplying identity matrix with 1 and 0. And if you multiply this on your own, you will get a 1 0. That means this function that you are seeing here, operation f of x equals to x, this f of x basically multiplying with the identity matrix. And what you are multiplying, your input is like, if the input is 0, you are getting 0. If your input is 1, after multiplication, you are getting 1. And for negation, we are using uh, like the same thing. We're just multiplying with what's that matrix called? I forgot. Permutation matrix. Yeah, this is just the permutation matrix of the identity matrix 0, 1, 1, and 0, 0, 1, 1, and 0. So we're multiplying with the permutation matrix and we're getting 1. If you multiply the permutation matrix with 1, 0, you will get 0, 1, which is 1. And if you multiply the permutation matrix with 0, 1, which is 1, you will get 1, 0, which is 0. Like the last slide here. 1, 0 means 0, 0, 1 means 1. So, okay, if we're okay with it, can someone just confirm that are you guys okay with till now or something? If you are listening.
Yes, it's okay.
Okay. Thank you. So, okay. So, uh, where was I? Yeah, the identity and the negation operation. Let's talk about two other operations. That is constant 0 and constant 1. It's like a box. It's the same. It's a function and it's a box. If you input, like if you put a 0 inside it, if it's a like constant 0 box or constant 0 function, you will always get a 0 no matter what the input is. Even if you like give me as an input in the box, you will get a 0. And if it's a constant 1 box or constant 1 function, you will always get a 1. There is no other option. So how does it work? This is also a permutation matrix. It's like the permutation matrix are designed in a way so that the function works. So constant 0, for constant 0, you will always get a 0, whatever your matrix is, whatever your input is. For constant 1, you will always get a 1, whatever your input is. So if you just try it yourself, it will take like 30 seconds to multiply these things, and you will see that you are getting 0 and 1. Let's go forward and let's talk about reversible computing. So let's just establish something first. Quantum computers only use the reversible operations. Like previously, the operations that we saw, these are classical operations. Like classical computer do these sort of operations to calculate whatever your program is or whatever the problem that you have given. These calculations are done on the basis of these operations. But quantum computers only use special type of operations which are reversible. Reversible means, I'll talk about it in a bit. And in fact, all quantum operators are their own inverses. That means if you inverse one operation, you will get the same thing. Like they're it's like they're like positive and negative in the same time or same space. So what reversible means is if you give an operation, like suppose you have a box, what reversible means is you have a black box that you don't know what's inside the box. You just put it an input and you get an output. And then if you don't know what's inside the box, then there is no way that you can track back the output and like find out what was the input. But if it's a reversible operation, that means if you have an output and if you have like a black box, then you can figure out or engineer some way to figure out what was the input. Like if you don't know what's coming inside a box and you are just getting the output, and if you know how the box is working or what the function is inside, then you will figure out a way to go from the output to input. That's called the reversible operations. Okay, let ax equals to b. If you know a and b, you can find out the value of x. X means the variable. X means the input that you are giving. A is the black box. A is the function which is acting on x and giving you the output b. And you are, if you know A and you know B, and you can figure out x. So permutable operations are reversible, and the operations which erase or override are not reversible. So what is permutable operations? Permutable operations means it can change, it can vary depending on the input. like the four operations that we have seen so far, identity and negations operations are reversible, because if we go back, identity operation, it's like if you put zero, it will always give you zero. If you put one, it will always give you one because it's identity. And the negation operation is like if you put zero, you will get one. If you put one, you will get zero. So you know what the function is doing. Like whatever the value you are inputting, it will negate it and then it will give you an output. So if you have a black box and something went inside it and it came out as a one, and you know the black box does the negation operation, then you know the input was zero because the output is one. And if you know the black box is an identity operation, then if the output is zero, you know the input was zero. But for constant one and constant zero, you can't surely say what is the input, what the input was, because whatever you are giving there, if it's a constant zero operation, it will always produce zero. And whatever you are giving inside a constant one operation, it will always produce one. So that's why identity and negation operations are reversible. Constant operations is not reversible. Okay. Uh, so let me introduce you to a new way of multiplying things. It's called the tensor product of vectors. There is nothing to be worried about. It's just simple if you just follow me here. So what happening here, like these are two metrics, x0, and the elements are x0 and x1, and the another matrix is y0 and y1. And if we do tensor product, by the way, the tensor product sign is like cross multiplication sign inside a circle. So if you do tensor product multiplication here or whatever, like tensor product, then what the process is like, you will have to first multiply the first element with the whole matrix and then the second element with the whole matrix. And if you do it by yourself, you will find something like x0 y0 x0 y1 x1 y0 x1 y1. It's like permutation, like you are doing permutation, if you know what I mean. And like for example, here you have like 1, 2, and 3, 4. If you multiply it, you will get 1 times 3 is 3, 1 times 4 is 4, then 2 times 3 is 6, and 2 times 4 is 8. So this is how it's done. And if you like we can do tensor product for multiple matrices like x0, x1, y0, y1, z0, z0, z1. So if you do it, it will be like x0, like it's the permutation of three it's a permutation of order 3 basically. So like 0 1, if you multiply 0 1 0 1 1 0, like you have to like break it first, like you have to take two metrics and break it like the upper one, like 1 2 3 4 metrics, and then you have to multiply it with another one. So you will get this number. You will get a matrix which is like of 8 elements here, if you can see this. So yeah, it's just a permutation matrix anyways. Now let's do the let's take two classical bits. Like remember, we used to represent like zero. We used to represent classical bit with like vector notations, like Dirac vector notations. So this is 0 0. That means we have 1 0. We can represent 0 0 with 1 0 times or tensor product of 1 0. So if we do it, we'll get 1 0 0 0. So it produce something. So this is 0 1, and if we write it like in tensor product, it will be like 1 0 and 0 1. And if we tensor product it, we'll get 0 1 0 0. These are like basic example of tensor product, how it works, like representing the multiple classical bits. how it can be represented with tensor product, and how we can write it in matrix form and use it to calculate like classical calculations and stuff. Will Why these are necessary, I'll talk about it in a while. So let's present 4. So what is this 4? This is a like decimal number 4, and if you represent it in binary, the binary of 4 is 100. So what does it represent 100? This means 01. This is 1, if you remember from the slide when we started, and multiplied with 0 and 0. 0 is represented by the matrix 1 0, and this is another 0. So if you multiply this, you will get a matrix of 8 elements, and this is the matrix that you will get. And this is how like all other numbers can be represented. Like if you take 5, 6, 7, 8, or any other decimal number, you can convert it into binary and put it into direct notation and do the tensor product, and you will get like you will get matrix with higher number. Like if you are noticing something here, like this is 3-digit binary number, right? So 001. And after doing the tensor product, we are getting what? 8 digits of a like 8 elements matrix, right? So I don't know if you are sensing something here, like exponential 2 to the power 3 is 8. If you are seeing something like that, then you are on the right track. That if you are sensing something like that, that means I have done my job till now. Okay. So let's see. These tensor representations are called product state. Product states can be factored back into individual state representation. So the higher order matrix that you are seeing here with 8 elements, it can also be factored back into individual state like 101001. It's reversible. This product state of n bits is a vector of size 2 to the n, which I just said a while ago, like a moment ago. So size is 2 to the power n. So if you have a n bit binary number, the product state will be 2 to the power n matrix, 2 to the power n state. So the product state would be, yeah, with 2 to the power n elements of a matrix. So this is important because this is going to help us understand why we need quantum computer and why quantum computer supersedes like classical computer. Okay, now let's talk about a new gate. If you are familiar with AND or XOR gate and stuff, uh, if you are not, it's completely fine. It's self-explanatory. So this is a control NOT gate. What does it mean, a control NOT gate? It means it takes 2 bit. It is like you can compare it with a function or a black box or just a random box. It takes 2 bit as an input and do some operations on the bits depending on how the bits are presented. So how it is going to be? So if the control bit is set to 0, then it does nothing to the target bit. Oh, so the 2 bits that it takes, one is the control bit and the another one is the target bit. So the control bit decides what operation has to perform on the target bit. So if the control bit is 0, then it does nothing on the target bit. If the control bit is set to 1, then it flips the target bit to its counterpart. So if the control bit is 1, and if you are putting like 2, we'll see some examples on the next slide. And this is how the control NOT gate represented. This is the basically this matrix represents the control NOT gate, and we'll see. For now, you just remember this and you just take it as okay. This is control NOT gate, and this is the equation that leads to this matrix. And when this control not is applied to a target bit, the result is familiar to the XOR gates. Like sort of familiar to XOR gates from classical computation. I'm saying classical computation, and because like in classical computation there is not enough use of control not gate, but it's one of the fundamental like gates for quantum computing. The most significant bit is the okay between the two bits that a control not gate takes. The most significant bit is the control bit, and the least significant bit is the target bit, because control bit decides what operation to perform. You can program you can write your own like control something like, yeah, I like someday I might write control Saddat gate. So what that can do, like if you it can take like 2 bits, and upon the control bit you can like I can write some function which will hammer the bit another one and do something like that. So if you are like if you understand this, you can write your own control bit. So yeah, that's it. uh, okay. And the one important thing to remember is the control bit never change. Control bit never changes. It stays like unchanged for like all the time. It's like a constant bit. Let's see how it operates. So C by C I represent the control like C naught gate or C naught operation, and this is 0 0. That means the C naught function is taking 2 bit as input, 0 and 0. The first bit is the control bit, and the second bit is the target bit. So what we are doing is we are applying C naught on these 2 bits, representing in the matrix form and tensor product, and these the large matrix that you can see here, the square matrix, it's the control not matrix, and these 1000 in the middle, the right middle side 1000 is the multiplication, is the tensor product of these two states. So if you apply the control not gate and if you multiply it by yourself, you will figure out that you will get a 0 0. And why 0 0? Because the control bit is 0, so it is not applying anything on the target bit, and you are getting the same result. And if I input like 0 and 1 in the control not gate, and the control bit is 0 and the target bit is 1, it stays the same. You can just do this calculation by your own. It's pretty simple. And let's see if we change the control bit to 1. So now we are giving control bit 1 and the target bit 0. So we do the same calculation, and after the calculation or after the process, you get 1 1. You see the target bit is changed right now. It changed from 0 to 1, and on the second calculation, the target bit changed 1 to 0. If you do it by your own, you will understand it better, because it's just calculation and how it works. Okay, so if we are good, are we good till now?
Yes, we think we are.
Okay. Okay, let me know if I am like going super fast or something, or like if you are missing something, just ask me. Okay, so summary so far, what did we learn? We have learned how to represent the classical bits as vectors like this, 1 and 1 0 for 0 and 0 1 for 1. And then we learned how to represent the operations on bits as matrix form. We learned all the operations used in quantum computers are reversible, like the thing that I said. Quantum computer only uses the reversible operations, and we can represent multiple bits as tensor product of the single bit vector. Okay, then the C0 gate, the reversible gate. C0 is a reversible gate, and it's a fundamental building block of the quantum computer that we got. So now let's dive into actual quantum computer and let's see what we need to do. So, surprise. So till now, what you just saw and what you just did, it was basically special case of a quantum computer. So whatever we did in a classical bit vector we have used so far are basically special cases of qubit vectors. So now let me like define what is a qubit. A qubit is represented as A and B matrix, where A and B are complex numbers, and they hold the property of A square plus B square equals 1. It's like the norm of A square plus B square equals 1. It's the probability, basically. It's the probability calculation. For example, like if we take like 1 over root 2, it's a complex number, and 1 over root 2, a complex number in a matrix, and we multiply it, like these are basically qubits, representation of qubits, 1 over root 2, 1 over root 2, 1 over 2, and root 3 over 2, negative 1, 0, 1 over square root 2, and negative 1 over square root 2. These are basically representation of qubits in matrix form. So these numbers are complex. The thing that we need to remember is that the qubit that we are going to represent in matrix are they have to be like a complex number. So yeah, these are complex number, and these are like basic representation of qubit. And let's talk about the superposition state. What does it mean, basically, superposition state? It means a qubit can be both 0 and 1 at the same time. This is where this is the main difference between a classical computer and a quantum computer. It means like in classical computer, a bit can only be 1 or 0. But in a quantum computer, a bit can be 0 and 1 at the same time. So that's basically the difference. And if we consider a qubit with value a, b in a matrix, then it has like a square probability of being 0 and b square probability of being 1. When a qubit is measured, it shows the value 1 and 0 depending on the measured state of a qubit. We'll talk about this in a moment so that you can understand. It means when measured in state 1, 0, that means 0 state will always return 0 with 100% probability. And if it's measured in the alternative state, that is 0 and 1, it will always return 1 with 100% probability. We can also represent the qubit using the Dirac notation, like we did for classical bit. Uh, there is alpha 0 plus beta 1, where alpha square plus beta square equals to 1. It's the same as a square plus b square equals to 1. So basically this is the probability of getting whatever value we are measuring on the state. Yeah, there you go. Alpha and beta are probabilities that determine the value of the qubit when it's measured. So, okay, let's see what's there. Okay, while using multiple qubit, we use tensor product. I'm not like we have seen how tensor product works. So for this calculation, A, B, and C, D, if we do tensor product, we'll get AC, AD, BC, and BD. What it does, basically, it shows the probability AC square plus AD square plus BC square plus BD square. These all are states on which we are measuring, states on which we are measuring the qubits, and those probabilities adds up to 1. And if we consider this system, these are actually representation of qubits. If we multiply these, like if we do a tensor product here, we'll get like 1/2, 1/2, 1/2, 1/2. And if we do 1/2 square, it's like 1, 4, 1, 4, 1, 4 plus 1, 4. It's like 0.25. Like the probability is 0.25. So it all like 4 of the states add up to 1. So what are the states that we have measured on? Like 0, 0, 0, 1, 1, 0, or 1, 1. It's the permutation of two digits, like two bits. 0, 0, 0, 1, 1, 0, 1, 1. It's like pretty basic. So let's see operations on qubit. How do we do operations on qubit? All operations on qubits are done by matrices that we have that I said before. So matrix operators are used to model the effect of the device which manipulates qubit spin or polarization without measuring the state. So uh, like this is one of the operation like it this is one of the permutation matrix that we saw in like classical operation 0 1 1 0, and this is the qubit, and we're applying this like matrix on this qubit and we're getting this result. So if you can see this, what's happening here is just flipping the qubit like it did before when we did like negation operation. So this is basically negation operation. If we apply this on this, it will just flip the bit. It will go 1/2 and square root of 3 by 2 to another matrix that is square root of 3 by 2 and 1/2. So that's how the operations are done on qubit.
স্যার,
And let's
আমরা একটা কোশ্চেন নিতে পারি রিলেটেড টু ইউর স্লাইড দিস স্লাইড। তাহসিন মুস্তফা, সো মাল্টিপল কিউবিটস ক্যান বি সেভারাল স্টেটস এট দি সেম টাইম। যদি এই কোশ্চেনের অ্যান্সারটা দেওয়া যেত।
multiple qubit, sorry.
So multiple qubits can be in several states at the same time. এটা কোশ্চেন ছিল।
Acha, multiple qubit can be in several states at the same time. Yeah. It's like I was talking about only one qubit just to make an example. Like one qubit, it can stay at 0 and 1 at the same time. So if we are taking multiple qubit, they can be in superposition state and they can be in multiple state at the same time. So that's why quantum computer do like quantum speed up happens. I'll talk about it in the later slides why this happens. I think uh, did I give your answer or okay, Tasin Mustafa. Okay. Let's see. Okay, we're done here with the operation on qubit. Can you see my slide?
Yes, দেখা যাচ্ছে।
Okay, now let's talk about the Hadamard gate. So what is Hadamard gate? It's basically the superhero of quantum computing. So why? I'll tell you why. The simplest definition goes like this. The Hadamard gate takes a 0 and 1 and puts it into exactly equal superposition. It takes a bit, like a classical bit, and it like puts it to the superposition state which is needed for a quantum computer. So what happens here, people sometimes they understand, or like there is this misconception among people that quantum computer will replace classical computer, but it's total misconception because quantum computer cannot perform or cannot work independently unless you are like operating it with a classical one. You have to like you have to get help from the classical one. It's not like it cannot work or it cannot function independently. So it's dependable on classical one. So what Hadamard gets do, it's like you write a program on classical computer that a classical computer can understand, but for a quantum computer, it's just gibberish. It's just like Klingon that people from Earth or people from another planet won't understand what Klingons are saying. So for an interpreter or for a translator, you need Hadamard gate to translate the classical instructions to quantum, to translate the classical bit to quantum, to its superposition. So what it does, it takes 0 or 1, a bit, a classical bit, and it puts it into exactly equal superposition, which is understandable by the quantum computer. And the Hadamard gate is represented by the capital H, and it's equals to 1 over root 2, and this matrix, like 1, 1, 1, negative 1. So it's like after, like, if you do the calculation and stuff, you will go to Hadamard gate and you will get this matrix. So how does the Hadamard gate works? It's like if you put a 0 inside a Hadamard gate, it will return you a superposition state of 0 plus 1, like with the equal probability of getting 1 or 0. And if you put 1, it's the same. It will give you an equal probability of getting 1 and 0. So basically the last box, what it says, it's true. The Hadamard is one of the unsung heroes of quantum computing. It's a simple looking gate, but harbors a remarkable property that, if you think about it, turns out to be of vital importance in quantum computing. Basically, till now, the way the quantum computer are architectured, till now how they are built, it cannot work without Hadamard gate. So Hadamard gate is the most significant gate for quantum computing. So we'll see how it works in later slides. So when the Hadamard gate acts on a computational basis state X, we understood like what a basis state in like previous slide. It transforms the input the it, according to the basis state. So Hadamard of X, like it's like 1/2 0 plus 1, 0 plus negative 1 to the X and 1. So it's this negative 1 to the X. This decides what this bit is going to be. Like, for example, if you like prepare n qubit, like if you take n number of qubit and in each state apply its own Hadamard gate in parallel, the state producing equal superposition of the integer is ranged from 0 to 2 to the power n minus 1. So the superpositions, the number of the number of state that is produced, like remember the state vector state that we got from the classical calculation. It's 2 to the power n. While doing some calculation on the classical bits. Now we are doing calculations on the quantum bits. So qubits, when we are applying this Hadamard gate to a qubit, we will get a state of like 2 to the power n minus 1, not 2 to the power n. It's like 2 to the power n minus 1. Like it's like for classical, we are getting 2 to the power n, and for quantum, we are getting from 0 to 2 to the power n minus 1 using the operation this. This is the operation that, like, for example, this equation, this is 0, 0, 0, and we're parallelly applying Hadamard gate on these like qubits, and we're getting this equation 1 over square root of 2 to the n and 2 to the n minus 1 summation where j, like gate of j is the computational basis state indexed by the binary number that would correspond to the number j in like base 10 notation. What it means, like if I give an example, you will understand. In 7 qubit register, if we take a 7 qubit register, the state 19, like to represent 19, we need to do this 1, 1, 0, 0, 1. Till now, with this 5 digit, we are good to represent 19. But we add this extra 2 zeros just to, so it's just a padding to make the binary number 7 bit in length. So this is what it does basically, to 0 to 2 to the n minus 1. So that's how it's done. And this is the state machine. I'm really sorry about the pictures. It's hand drawn. I drew it, and I'm not a like I'm literally suck at drawing. So this is the unit circle state machine. If you remember from high school trigonometry, like we had a unit circle of length 1, unit circle of 1, which radius was 1, and then we could like map all the angles around that circle. So this is basically the same thing, but we are doing in quantum computing with state machines to define the transpose or the transformation of the qubits. How it's done, like from 0, 1 to 1, 0. 0, 1 means 1 and 1, 0 means 0. If we consider this x-axis, 1, 0 on the first circle where it's written x, and the y-axis 0, 1, like it's 1, so it's reversible. It's just you can reverse it to 0 to 1, 1 to 0, and the superposition state, which is a quantum, like for a qubit here in the middle, either it's 0 or 1, and if you like do it, like if you change it or if you flip it, you will get the same thing, 1 over root 2, 1 over root 2. If you flip the matrix, you will get 1 over root 2, 1 over root 2. It's the same. So this is the X operation that's being applied on these matrices, and then this is the Hadamard gate that is being applied on these qubits. So from 1, 0, if we apply Hadamard, we are going to 1 over root 2, 1 over root 2. And if we apply Hadamard on 1 over root 2, 1 over root 2, we can map back to 1, 0, because this is reversible. And remember what I said before, quantum computer always like quantum computer always uses reversible operations. And if we do like 0, 1, that is 1, and we apply Hadamard, we get 1 over square root of 2 and negative 1 over square root of 2. It's like negative 1 and stuff. So this is the unit circle state machine, and this is how it works. So you take an input 1, 0, and you apply the X operation over it, and then a Hadamard, then another X operation, then another Hadamard, then another X operation. You get negative 1 over 0. How does it work? If you can follow me on the circle, uh, can you see my cursor moving?
Yes.
Okay, that's cool. So if you take 1, 0 and you do a X operation, it takes you here to 0, 1. And then on 0, 1, you do a Hadamard operation that takes you to here, 1 over square root of 2 and negative 1 over square root of 2. Then here you do another X operation and it takes you to here. And then from here you do another Hadamard, it takes you here. And from here you do another X operation and it takes you here. So it's like playing with a circle or playing with a ball with multiple points. And like if you are from physics background, and if you know what is antipodal points are, so these are basically antipodal points, and these are antipodal points. I consider it, like I call it antipodal points. I don't know what other like experts call these things, but for my understanding, I call it antipodal points. So uh, by applying X operations and Hadamard operation, you can basically play with this diagram and go from one to another, like transforming things. So this is how a unit state machine works. Now we have now we are basically done with how a quantum computer or basic operation works. Now let's see it in action. Basically, then we will basically outperform a classical computer here with this Deutsch oracle problem. What is this Deutsch oracle problem? It's the simple definition is like, so there is a black box, like this is the black box, which takes a bit as input and applies some mysterious function on it and returns an output bit. this is a black box. Like before I said, it takes an input from here and gives an output. And you don't know what the function is inside this black box, but you need to figure out the function. And this is how we're going to beat a classical computer. Let's see. We input some bit into a black box to generate some output. The question is, how many queries do we need to determine the function inside the black box on a classical computer? Like, how many inputs you have to put in here and how many outputs you have to measure to figure out what's inside this black box? Like, what is the operation that is being acted on this input? And like, how many do we need for a quantum computer? Like, how many what's that called? Like, how many input and output we have to figure out for a quantum computer to understand this property of black box? We want to determine whether the function inside of a black box is constant function or a variable function, because I talked about only like only four functions. I'll work with those four functions, and with these functions I'll beat a classical computer. Let's see how it works. So I talked about the constant 0 and constant 1 function, and my question is, how many queries would it take for a classical computer to determine if it's a constant 0 or constant 1 function? If you can remember, I told before that like the negation and the identity functions are the variable functions. So there are two group of functions. One is the constant 0, constant 1, and then there is another group of function which is a variable function. It can be like uh, what are those functions? Those are like the negation function and the identity function. So remember these two groups. And that's the question, like how many query it would take for a quantum computer to figure out. And to do that, we have a black box. We have the black box right here. And we're going to add some wire to it to measure the function, like what's happening inside. How do we do that? We rewire the black box in a way the input stays the same. Like we put an input here, the input stays the same. The input prime, if you can see, it's written input prime and it's the basis of x, it's the same. We put an extra wire that carries an output that's in 0, like it's in state 0, and we figure out this function over here as the output. What happens to that output? Let's see. Simply we add an additional output qubit to the black box to which the function actions will be applied. The black box writes the function to the additional output qubit, leaving the original input qubit unchanged. So what we are doing, we are now giving the black box two wire. One carries the original input, and after getting out of the black box, it stays the same. And we are fooling the black box to act upon the input that we are giving it with another wire, and we are considering it as output. So the input that the original input stays the same, but we are fooling the black box to act upon the output bit that we are giving, and on which we want the black box to act upon. So this is the output bit, and this is the output that we will examine, and this input stays the same. Okay, so this is just the same diagram. Okay, let me ask you a question. So if we are giving output 0, and here, if you can see my cursor circling around here, f of x, if we get here 0, then what function it can be? Like, what is the operation that it indicates? Can anyone like answer, please? let me rephrase the question. Like, suppose you are giving input here. I'm not taking that input. The x stays the same. Here, I'm giving a 0, and after this black box is doing something inside mysterious, I get an output which is also 0. So, for like, what hits your mind first? Like, what function is acting on it? Uh, Hello, hello. আমার কথা শোনা যাচ্ছে?
Yes, শোনা
See
যাচ্ছে।
the chat.
Okay. Okay, yeah, this is the one, constant 0, I think. Yeah, that's the one. So yeah, okay. So if we get 0 here, that would be constant. Like, that indicates the constant 0. Now, if we get 1 here, whatever the input we give here, like this, the original input stays the same, and we put something new here, and like 0 or 1, there is no other thing that we can put here, like 0, either 0 or 1, because that's the basic state of like qubit for understanding this problem. So if we put 0 and if we get 1, that means it's like giving, I put for input, I'm giving it 0 and it's returning me 1. That means it's constant 1. It's like acting on the 0 and it flipping it and giving me 1. That's constant 1. And if we got 0 here, that could be like identity or something like that. Let's see. And it can go vice versa, like for constant 0, for input 1 here, if we get 0 here, that would also mean that it's constant 0. Okay, why identity? I'll tell you why. Identity, because what did we know about identity? If you put 0, you will get 0. If you put 1, you will get 1, right? That's the identity operation. Okay, let's go forward.
Yes.
Okay, the Deutsch Oracle identity. Now, the identity operation. Let's see how it works. Okay, this is basically the circuit that represents the identity function. How it's done, like here, the input is X and the output is also like this original input stays the same, and whatever the input I give here, I'll always get X because it represents the identity relation between this and this. Like this black box, like basically whatever input I am giving it, it will give me that. So this is the identity function, and this is the negation function basically. So whatever the input I'm giving here, a control NOT gate will apply here, and it will flip the input and give me the negation of the original input. Like this is how the negation function works. If you can like follow this slide and work out yourself with these circuits, you will understand it's pretty basic. And let's put together everything in one circuit, what it did. So this
Actually,
is
can I
the,
interrupt you, sir? Can I interrupt you?
yeah,
I have
sure,
a question. You just provided 4 circuit actually. The negotiation, identity, constant 0, constant 1. This is the basic circuit for quantum computing, or there are more circuit? Actually, this is
there
the
are
basic.
more,
Yeah.
there are other circuits, but these are the elementary circuits basically.
Yeah, like NAND and NOR gate.
Yeah, like
Yeah,
like
thank you,
you
thank you.
can build up things with these elementary
Okay,
circuits.
thank you.
And I also talked about these circuits only because the Deutsch Oracle problem is the simplest one to explain. And for Deutsch Oracle problem, these elementary circuits are enough.
Yeah, I
So,
understand.
okay. So let's put together everything in one circuit. Let's see what happens. So in this circuit, what's happening here? So this is our input, the original input, and we're applying an X operation over it and then a Hadamard to make it a superposition state. And then we are putting into the black box, which is a quantum computing like system. And we're giving it another input, which is our defined input, and we're applying the X operation on it and then a Hadamard. It's the same operation and putting it on in the black box, and we're getting the output. So remember I told you the Hadamard is a reversible gate. So when we are inputting it into the quantum computer, then we're applying the Hadamard and putting it into the superposition state. And then when it gets out of the black box, we are applying Hadamard again to take it back from the superposition state to its classical counterpart. And then we are measuring this is basically the measuring circuit. We are measuring the qubit, what the input or output is basically. So, okay. Uh, okay. So let's see how we can obtain our result by only one query from uh, like okay, let me explain it first, then I'll say why. So first we need to pre-process the qubit that I already explained, X gate and Hadamard gate. Now inside the black box, we apply the function on the qubit superposition state. Like post-processing qubit, that's the same. Like I said, we do a Hadamard gate again, and then we get the qubit, we measure it. Okay, expected results. After measuring the qubits, if the black box function is constant, like if the black box function is doing constant operation, it will be in state 1-1. Why 1-1? Let's see. Okay. If the black box function is variable, that means I told you there are like two group of operations that I discussed. One is constant and another one is variable. What are the variable operations? That is like identity and the nation, right? And the constant operations are constant 0 and constant 1. So if it's constant operation, then the output will be 1-1, and if it's variable, it will be 0-1. Okay. Yeah, okay, here. We put a 1 here and we put a 1 here. And after measurement, these original input will be the same. And we said, like, okay, where was that? Where is that? If we put a 1 here and a 1 here, the original input will be the same. And the output, if 1 comes out, that means it's a constant function. That means either it's a constant, either it's like it's the basically it's the constant function because we are putting it one here and it's giving 1 here. And if we put a 0 here and if we get a 1 here, then what happens? That means there is something basic uh, there is something is changed in between, right? Because we are putting 0 and we are getting 1. And if we put 0 here and it stays the same, so the original input is not our concern. The second bit that is coming out of the black box, that's the most important bit for this Deutsch Oracle problem. for a classical computer, this will take 2 steps to verify. It's a constant function or a variable function that's like inside this black box. But for a quantum circuit, if this is if this is a feasible quantum circuit, and if you work on it, like putting one portion, you can like figure out if it's a constant or a variable function. So that's where we are beating the classical one by okay. Yeah, that's why we are beating the classical one in single qubit. Like the Deutsch oracle works for a set of qubits. It's not like general version. So there is like another version of it that is called Deutsch-Josa problem. So Deutsch-Josa problem, it has a 8 black box system. So it can take up to n bit, and it can determine if the function is constant or variable. This another version of this Deutsch oracle problem, and if we consider it like the n bit problem, and if you consider the circuit that I showed you, it's like for classical computer we need 2 queries to do that, and for quantum computer it takes 1 query to do it. So it's basically 2 to the power n, it's basically 2 to the power n inputs, like what it says here, which means it can determine whether the function returns the same value for all 2 to the power n inputs. Why 2 to the power n inputs? Because it's the vector state when you like do tensor calculation and stuff. Okay, so this is where everything from classical computer shatters, and this is where it ends for classical computer. The Shor's factoring algorithm was also inspired by the variation of Deutsch-Josa, like variation of it. There is this typo here. There should be it in here. The Deutsch-Josa problem. This Deutsch-Josa problem, which is like n-bit black box system, the Shor's factoring algorithm was inspired by Deutsch-Josa problem. And so far, what we have done is like how to represent computation in basic algebra reversing qubit. And yeah, so what I was talking about is just in the state of the calculation. It's just it goes exponentially. If you have like 3 qubit system, the state of the vector or the state of the matrix that you will be calculating with, it will be 2 to the power 3, so 8. So you will be able to calculate the same amount of calculation that a classical computer does with 8 qubit system with a 8 classical bit system. On a quantum computer, you will be able to do the same amount of calculation with 3 qubit system. So if you have like a classical computer with 16-bit system, you will be able to do the same amount of calculation with 4 qubit quantum computer. So this is where quantum computer beats classical computer. If you increase the quantum, like if you increase the qubit in a quantum computer, you will be able to like surpass the whole universe basically, because up to 52 qubit system, 54, someone wrote it down in the comment. Google used 54 qubit system to like claim quantum supremacy. If you calculate 2 to the power 52, I don't know what that number is. It's gigantic, I think. So that many classical bit will be need like for calculating the same amount of like calculation in a classical system. So for basically, if you have a classical system with 124 qubit, the same amount of calculation you will be able to do in a quantum computer with only 10 qubit. I think 2 to the power 10 is 124. Yeah, if that's like if my calculation is correct, so 10 qubit system. So that's why the exponential speed up happens, and that's why quantum computer like shatters classical one. So To understand this Deutsch Oracle problem is the simplest one, and I tried to put it very simply. I don't know how simple it was. Like, I don't know if I have bored you or something, but yeah, this was it for today. So thank you for tolerating this part. And also, I have put an appendix here where you can see the calculation of Deutsch Oracle identity problem. So it's just basic matrix calculation. You'll be able to do it by yourself. And if there is a way that this slide can be posted somewhere, or if you want it, you can email me. I have my email address written on the first page of the slide. So yeah, thank you. Thank you very much, everyone, for
আমরা অনেক কিছু জানতে পারলাম এই কোয়ান্টাম কম্পিউটিং সম্পর্কে এতক্ষণ ধরে। তাও আমাদের কিছু ডিসক্রিপশন, আমরা ব্রিফ ডিসক্রিপশনে কিছু প্রশ্ন করতে চাই, শুনতে চাই আপনার কাছ থেকে। শোনা যাচ্ছে?
জি, শোনা যাচ্ছে।
আচ্ছা, প্রশ্ন করতে চাচ্ছি যে আমরা তো এতক্ষণ ধরে আমরা পুরো সিস্টেমটা কিভাবে কাজ করে, কোয়ান্টাম কম্পিউটিং, ম্যাথমেটিক্যাল অনেক কিছুই দেখলাম, যারা আমরা ইঞ্জিনিয়ারিং সেক্টরে পড়াশোনা করছি, এটা আমাদের জন্য নতুন কিছু না। তো এখানে আজকে যারা অডিয়েন্স এবং পার্টিসিপেন্ট আছেন তাদের পক্ষ থেকে প্রশ্ন করতে চাচ্ছি, যারা বিগিনার, ইন্টারমিডিয়েট লেভেলে আছে কিংবা এখন রিসার্চের দিকে তারা কাজ করছে এখানে। তো সবার কাছ থেকে যদি বলতে চাচ্ছি, আপনি নিজেও রিসার্চের কাজ করেছেন, তো এই ফিল্ডে কাজ করার আগে, মানে শুরু করার আগে আমার কি কি দক্ষতা আমি অর্জন করব, বা কোন কোন জায়গাগুলোকে আমি রাখবো যে আমি যখন কোয়ান্টাম কম্পিউটিং নিয়ে কাজ করছি, এই বিষয়গুলো আমাকে মাথায় রাখতে হবে, যদি একটু বলতেন।
Okay, so I can only tell, I can only talk for myself how I started and stuff.
Okay.
So first of all, আমাদের okay, so senior year থিসিসের সময় যেটা হয়েছিল যে we were searching for something like interesting to do, and আমাদের যে সুপারভাইজার প্রফেসর ডক্টর মাহবুব মজুমদার, তিনি আমাদের I think এখানে সনেট আছে, সনেট was one of my thesis mate here. So আমরা যেটা আমাদেরকে কোয়ান্টাম কম্পিউটিং এর সাথে ইন্ট্রোডিউস করায়, and we studied there, but honestly আমাদের থিসিসে we couldn't do much. আমাদের যে expectations ছিল, we couldn't do much, but I pursued it later, and I started exploring things, and there are multiple books, like মার্মিনের একটা বই আছে, author named Marmin, so quantum computer science. Just a second. Sorry, I'll show you the book. So it's like I started with basic book, and Marminer, yeah. If anyone wants to start, he or she can start with this book. It's pretty basic, and it's a small one. I always like small one and condensed books. So yeah. Right now, what I'm learning is like quantum information theory and black hole information paradox. It's basically a bit with like black hole physics and stuff. But quantum computing এর জন্য যে কোনো একটা বই শেষ করাটা জরুরি, to understand how it works fundamentally, and to understand where to go from there. You have to finish one book, at least one book. That book can be any book. You have to finish one book, and then you have to read the recent papers, and like the recent research articles that are being published and stuff. You have to keep track on that, and you have to understand what is going on right now in the field. Like I can share an experience. Like I went I was fortunate to be in a school in NTU Singapore, where that was a quantum computing school, and there I met with professors who basically work in the field. So there was one professor named Matthias Troyer. He's from ETH Zurich, and right now he's তার সাথে আমার like মেইলে contact আছে এখনো, and right now he is leaving ETH to work on Microsoft's quantum computing facility. So what he said one day that like like struck in my mind, that he said he can write program that is the fastest, that can beat the fastest computer program that exists in the universe right now. I was shocked. Then I dig into it and I asked him how do you do it and how stuff, and he said basically it's just quantum circuits, nothing else. If you can design quantum circuits optimized way, then you will be able to beat anything. Like classical computers will shatter in front of quantum ones. So uh, that's where my interest grew a little more, and then basically it like for a beginner you have to finish one book and you have to understand what it's saying, like that's it. Then you will be able to explore the things. Then you will, if you go for like another book, another author, you will be able to understand the perspective of that author, and you will be able to understand what a scientific paper is saying about this thing. But yeah, definitely you will be learning new things. Like right now আমি এখনো কোনো একটা পেপার পড়লে আসলে একবারে বুঝতে পারি না যে what it's saying or what the author is trying to express. আমাকে ওইটা মাল্টিপল বার পড়তে হয়, প্লাস ক্যালকুলেশন গুলো নিজে হাতে করতে হয়, এন্ড রেফারেন্স বই খুঁজে খুঁজে দেখতে হয়। অনেক সময় অনেক টপিক আছে যে আমি নিজেও এখনো বুঝি না। আমি সব তখন যে আমার সুপারভাইজার আছে তার সাথে দেখা করতে হয়, তাকে নক করে বলতে হয় যে ক্যান ইউ হেল্প মি উইথ দ্যাট। তারপরে আমার যে ফ্রেন্ড সার্কেল আছে তারাও, আমার ফ্রেন্ড সার্কেলে বেসিক্যালি উই হ্যাভ দিস গ্রুপ, কোয়ান্টাম কম্পিউটিং গ্রুপ, লাইক ইটস কাইন্ড অফ ইনার সার্কেল ইন ব্র্যাক ইউনিভার্সিটি। ওখানে অনেক ফ্যাকাল্টি আছে যারা কোয়ান্টাম কম্পিউটার নিয়ে কাজ করেছে প্লাস করছে এখনো। তাদের সাথে কথা বলে গ্রুপ মিটিং এ এটাকে ডিসকাস করা যে হাউ দিস ফাংশন ইজ গোয়িং, হাউ দিস ফাংশন ইজ ওয়ার্কিং। সো এইগুলা নিয়ে আসলে মানে সবার সাথে কথা বলে বলে দেন আমাকে এইগুলা শিখতে হয় এখন। and most important thing is that first you have to finish one thing, one book, so that you can go from there. Like you have to start somewhere. That's it. That's the main thing. যেমন আমি আন্ডারগ্রেড থিসিসের সময় I didn't finish any book, honestly speaking. Then later on I finished a book, and then I understood where I was lacking behind and where to go now and what to explore now. So yeah, that's the thing. You have to, like, yeah. I think, I mean, আমার কেসটাকে আমি প্রেজেন্ট করতে পেরেছি, and I think you will be able to relate it to your case.
আরেকটা প্রশ্ন, যেটা যখন এখন একটা প্যান্ডেমিক সময় চলছে, পোস্ট প্যান্ডেমিক আইটি সেক্টর অর দি পোস্ট প্যান্ডেমিক ওয়ার্ল্ড, হ্যাঁ, নিউ এভলিউশন, তো নতুন পৃথিবী নতুন সবকিছু। তো সেই ক্ষেত্রে যদি বলতে হয় যারা এই কোয়ান্টাম কম্পিউটিং এ কাজ করতে চাচ্ছে তাদের জন্য, যে অনেকে ক্যারিয়ার নিয়ে ভাবছে বা অনেকে রিসার্চ করবে, যেমন আমরা প্রথমেই স্লাইডের শুরুতে দেখছিলাম যে আপনারা কোভিড-19 এর এই ক্ষেত্রে এটা আমরা বায়োটেক ইন্ডাস্ট্রিতে বা আমরা এই জায়গাটার দিকে এটা কিভাবে ব্যবহার করতে পারি তার ইউজেস দেখছিলাম। আর আরেকটা কথা ছিল যেটা হচ্ছে কোয়ান্টাম সুপ্রিমেসি, ওয়্যার গুগল, নাসা, ইন্টেল, আইবিএম, মাইক্রোসফট সবার এরকম এই ক্ষেত্রে একটা বিশেষ ইয়ে আছে, সবাই এটা নিয়ে কাজ করার জন্য উঠে পড়ে আছে বলা যায়। তো এই ক্ষেত্রে আপনি যারা আসতে চাচ্ছেন নতুন এই জায়গাটায়, তাদের জন্য কি বলবেন আপনার ইয়ে থেকে?
Well, I don't know if I'm the right guy to like talk about like future plan and stuff, because I'm still here. I haven't done anything significant anyway, so I can just point it. Whatever this post-pandemic world, or like this pandemic, is not gonna affect like this area of research. Like I'm pretty optimistic about it, because like this doesn't collide with the world that is being affected. So and এই সময় আসলে আর the thing is that quantum computing is still booming. It's in very infancy period right now. It's not even a like working. There is not even a working like no one can claim that they have a working quantum computer in their facility. Not even Google, not even NASA, not even like Lockheed Martin, and not even Microsoft or IBM. They have like the adiabatic simulation system which they claim that they have simulated this much qubit and they have like achieved this much supremacy and stuff because quantum computing is a huge investment thing and একটা কোয়ান্টাম কম্পিউটার আগে যেমন শুরুর দিকে ক্লাসিক্যাল কম্পিউটার ছিল অনেক বড় বড় হল রুমের মতো লাইক ইফ ইউ সি লাইক ওল্ড পিকচার্স অফ ক্লাসিক্যাল কম্পিউটার অনেক বড় হল রুমের মধ্যে অনেক বড় বড় বাটনওয়ালা ছিল লাইক for like in advancement of the silicon chips right now এখন অত বড় হল রুম লাগে না কিন্তু একটা কোয়ান্টাম কম্পিউটারের জন্য একটা বড় সড়ো ল্যাব দরকার হয় কারণ কুলিং সিস্টেমটা এত সফিস্টিকেটেড হইতে হয় যে -0 মিনস -270 ডিগ্রি ক্যালভিনের নিচে কুল মানে কিউবিট গুলাকে ঠান্ডা করতে হয় সো কুলিং সিস্টেমটা অনেক বেশি সফিস্টিকেটেড হতে হয় ইভেন quantum computing facilitates the cooling system. That's the coolest place in the universe. Not even space is that much cooler. Like it's below like -273 degrees. So আর এটা অনেক বেশি পাওয়ার কনজিউমিং সো আর এইটার এখনো অ্যাডভান্সমেন্টের অনেক স্কোপ আছে লাইক যারা সফটওয়্যার ইঞ্জিনিয়ারিং করে কিংবা যারা কম্পিউটার সায়েন্স থেকে আসছে তাদের জন্য এটা তো কোয়ান্টাম সফটওয়্যার ইঞ্জিনিয়ারিং অ্যান্ড কোয়ান্টাম কম্পিউটিং এর যে অপারেটিং সিস্টেম অ্যান্ড স্টাফ এইগুলা ডেভেলপমেন্টের অনেক বেশি চান্সেস আছে আবার যারা ট্রিপলি ব্যাকগ্রাউন্ড থেকে আসতেছে তারা এই ইঞ্জিনিয়ারিং লাইক কোয়ান্টাম কম্পিউটিং এর যে ইঞ্জিনিয়ারিং সাইড গুলো হার্ডওয়্যার সাইড গুলো লাইক প্রসেসর ডিজাইন তারপরে কুলিং সিস্টেম ডিজাইন এই জিনিসগুলোর উপরে ফোকাস করতে পারে অ্যান্ড যারা একটু ম্যাথমেটিক্যাল ব্যাকগ্রাউন্ড থেকে কিংবা পিওর কম্পিউটার সায়েন্স ব্যাকগ্রাউন্ড থেকে তারা থিওরিটিক্যালি কাজ করতে পারে যেমন কোয়ান্টাম অ্যালগোরিদমস নিয়ে কোয়ান্টাম অ্যালগোরিদম জু নিয়ে যেমন I would like to like I know professors who are working on quantum computing and like researchers who work like they carry out state of the art research in quantum computing. One of them is Scott Aronson. Scott Aronson is the basically superhero in complexity and algorithm theory. So the complexity that I showed, it was defined by Scott Aronson, and Scott Aronson is a professor and he's working on theoretical quantum computing and building the complexity classes and algorithms and এরকম আরো অনেকে আছে এখন এখন অনেকে ডাইভার্ট হচ্ছে কোয়ান্টাম কম্পিউটিং এর দিকে even if you are from physics background, Leonard Susskind, the prominent professor who works in general relativity, he is working with Scott Aronson nowadays on complexity theory, on Harlow-Hayden problem and black hole information paradox and Hawking radiation. So these are all related. So yeah, and why এখন কম্পিউটার সায়েন্স এন্ড ফিজিক্স এর অনেক ব্রাঞ্চই এখন ক্ল্যাশ করছে কোয়ান্টাম কম্পিউটিং এর মধ্যে যেমন ব্ল্যাক হোলের যে ব্রাঞ্চটা ছিল আগে লাইক ব্ল্যাক হোল ফিজিক্স এন্ড লাইক জেনারেল রিলেটিভিটি দিস ওয়াজ লাইক পিওর ফিজিক্স পিপলদের জন্য কিন্তু এগুলো এখন কোলাইড করছে কোয়ান্টাম ইনফরমেশনের মধ্যে অ্যাজ লাইক যে ব্ল্যাক হোলের মধ্যে হকিং রেডিয়েশন ডিফেন্স যে একটা one bit of information falls into the black hole and another bit comes out. So if we can figure out if those two bit of informations are entangled together or sorry in superposition, then we can measure them out. And to do that, quantum computer is the like quantum computer theory is the most prominent one. So yeah, this is how things are coming out right now. যারা শিখতে চান কোয়ান্টাম কম্পিউটিং আর কোয়ান্টাম কম্পিউটিং এর যেমন আমি আপনাদের একটা কথা বলি there will be a school I got invited this year like কিসকিট IBM এর যে কোয়ান্টাম কম্পিউটিং ফ্যাসিলিটি আছে ওরা কোয়ান্টাম কম্পিউটিং এর জন্য একটা ল্যাঙ্গুয়েজ ডেভেলপ করছে it's under development right now it's called কিসকিট so কিসকিট 2020 একটা সামার স্কুল হবে আপনারা যদি সার্চ করেন গুগলে you will find it So Qiskit 2020 তে আপনারা অ্যাপ্লাই করতে পারেন this for the pandemic, this year it's free and like it will be online. So I hope সবাই এটাতে জয়েন করতে পারবে। আমি গতকালকেই এটার ইনভিটেশন পেয়েছি। সো ইয়া, ওইটা আপনারা শিখতে পারবেন। ইটস বেসড অন পাইথন। সো যারা পাইথন একটু একটু জানি তারা তাদের জন্য ডাইভার্ট করা কনভার্ট করা খুব ইজিয়ার হবে এটার জন্য।
আমরা ইন্ডিয়ান আর্টসের অনেক কিছু জানতে পারলাম যে অ্যাবাউট যে যারা রিসার্চ করতে চাচ্ছে, যারা এই ফিল্ডে কাজ করতে চাচ্ছে, অনেক ক্যারিয়ার অপরচুনিটি আছে এই ক্লাউড কোয়ান্টাম কম্পিউটিং এর ক্ষেত্রে। তো এই মুহূর্তে আমি একটু যারা চ্যাট বক্সে অনেক কোশ্চেন করেছেন বা কারো কোনো প্রশ্ন থাকলে করতে পারে, আমরা এখন প্রশ্ন নিব। স্যার আপনি যদি একটু চ্যাট বক্সটা চেক করতেন।
হ্যাঁ, শিওর। I don't think your question করছে or something.
আর কারো কোনো প্রশ্ন থাকলে করতে পারেন। শেষের দিকে রিকি Silasas, please show us some platforms where we can learn and practice and simulate.
Okay, for some platform. Okay. Is there any possibility to solve NP complete problem in speech? Oh, if okay, that's the question everyone is asking. So I don't know that answer. If the NP complete problems are solvable, then everything will just collapse. Like that is one of my interest, and I am trying to learn. So I don't know that answer. Sorry to disappoint you. If are you still seeing my screen?
Yes, দেখা যাচ্ছে।
আচ্ছা, so this is a platform where you can learn to program quantum computer, and also you can simulate your program here. This IBM Q account. What IBM Q is, I'll tell you what IBM Q is. IBM Q is a quantum computer that is developed by IBM, and it publicly made available of 10 qubit or 12. I'm not sure about the number right now. So they are run in cloud. So if you simulate the circuit, if you design algorithm, you can like simulate your circuit here, and you can solve problem also here. Like okay, so this is their IBM Q, I think, the image. I'm not sure though, because I don't come here much anyways. So there, the machine learning materials and optimization problems, yeah. So they're working on it. So IBM Q and Qiskit, you can try these things. Like they're pretty fun. Like once you get a hang on it, and you will see why it's so fun.
স্যার আমরা আমাদের ওয়েবিনার একদম শেষ দিকে চলে আসছি। তো বলা যায় ইট ওয়াজ অ্যান অ্যামেজিং ওয়েবিনার, ম্যারাথন ওয়েবিনার বলা যায়, and nice presentation.
Yeah, I'm really sorry about the timing because
it's okay.
Yeah. Okay.
অনেক কিছু জানতে পেরেছি।
When I was like planning for the session, I made like 97 slides, and I cut it to 47, I think. So
in a brief, অনেক সুন্দর একটা প্রেজেন্টেশন ছিল আমাদের, আমরা অনেক কিছু জানতে পেরেছি। হোপফুলি যারা আমাদের সাথে আজকে অডিয়েন্স পার্টিসিপেন্ট যারা আছে বা ছিল, তারা অনেক কিছু জানতে পেরেছে। তো স্যার আজকে ওয়েবিনারটা এখানে আমার শেষ করতে হচ্ছে। আমি এতক্ষণ ছিলাম হোস্ট ফারহাজা বিন ঐশী। আর এই একটা সময় আপনার ব্যস্ত সময় থেকে আমাদেরকে একটা সুন্দর সময় দিলেন, আমরা অনেক কিছু জানতে পারলাম আপনার কাছ থেকে। থ্যাংক ইউ স্যার। আর
Okay,
যারা
you are
অডিয়েন্স
welcome.
আমাদের সাথে ছিলেন
And
সবাইকে থ্যাঙ্কস। আর আপনি
thank
যদি
you everyone. Thank you everyone for like literally tolerating me this long, and
no, yes,
and
it's quite interesting.
I'm sorry if I have bored you or something, and there was like 2-3 typos in my slide. I'm really sorry for that. And ask the host, please. Is there any way that I can share this slide with like people publicly available? If you want, I can like email it to you.
আমাদের সাথে আজকে যারা ছিল পার্টিসিপেন্ট হিসেবে ছিল আমাদের এই মিটিং এর সাথে, তাদেরকে আমরা যেহেতু আমাদের ওয়েবিনার লিংকটা পাঠিয়ে দিয়েছিলাম, তো ওই স্লাইডটা থাকলে আমি অবশ্যই দিয়ে দিব। আর প্রয়োজনে আমি আমাদের যে ইভেন্ট পেজটা আছে ওখানে আমি স্লাইডটা অ্যাটাচ করে দিতে পারি লিংক থাকলে। শিওর।
ওকে, আমি আপনাদের স্লাইডটা মেইল করে দেব।
আচ্ছা ঠিক আছে, থ্যাংক ইউ সো মাচ।
থ্যাংক ইউ।
আজকের মতো আমাদের ওয়েবিনারটা এখানে শেষ করছি। সবাই ভালো থাকুক, স্যার আপনিও ভালো থাকবেন।
আচ্ছা, আসসালামু আলাইকুম।
ওয়ালাইকুম আসসালাম।